Cool. Okay, so here's the first question, and I want you guys to see whether you guys still remember that. So I'm going to erase some of what we did last time, and so this, I only have two questions, essentially. The first question is that if I have YLM, this is YLM, that's what I have here. What we call this is L. What we call this L is called turbine.
That's just the spin, right?
No, not spin. This L.
I'm trying to remember what it's actually.
Okay. Yeah. Think about it. What we call this M. What we call the L.
That's the magnetic quantum number.
Of course. M is a magnetic quantum number. Make sense? L is just regular orbital quantum number. That's it.
Orbital quantum number.
Or you could say orbital quantum number because you want to distinguish with it from spins, which is we haven't covered it yet. So
Wait,
this is.
Why don't we use N anymore? Because N used to be.
That's extreme great question, Cody. So you see now we have N disappears, right? We have complete N disappears. And in the beginning we have the N's, but now we do not have N anymore. It's just like a LM like this. And you're going to see shortly N will shows up quickly. This N shows up as very strange because did you see all these equations has no N? There's no N whatsoever. There's no N. It's just basically there's no N. You see it's always Ln. So there's no N. So we will keep that in mind. And why this happens? This is just a magnetic winds. So magnetic of angular momentum quantum number. So that's good. Now, how do we get from this one to another new ones like this? Suppose I know Ln, but I want to compute L prime M prime. How do we get that?
Use L plus or L minus.
Exactly. We can use L plus hat, L minus hat. So that's kind of give us the results. So this is essentially the key idea was that if you know the Ln, you can get L prime, L prime. So that is what we have. All right. The third question is the following. So this is you guys answered very well, which is really, really good. Now, next question, which we're going to ask you guys, third one. When we derive, you remember, when we derive YLL, when we derive this YLL, we utilized L hat plus LZ like this. But we did not use, we might eventually actually convert. We used this guy, we did not use this. You remember? What's the reason? Aisha, why we use this instead of this?
They're not permutable.
They're not permutable, and what's the other reason? Let me give you a little hint. What happens if I apply onto YLM? Do we know the results if this operator upon YLM? No, we don't know the results. And Cody, what is the results if we apply this operator on YA? In other words, we say this is better, but what you get from this one here? Still remember? Look at the notes, look at the notes, look at the notes. Why we use this instead of the bottom one, which we clearly, any ideas? Tell me, can you help? Why we use the top one and not the bottom one? Remember that? Okay. Let me give you another hint, Cody. If for LZ applying to this, what you will get? It was LZ applying YL equals what?
Is that 0? No.
Image bar.
Sorry?
Image bar.
Exactly. Cody, make sense? if you apply the spherical harmonic of the spherical, and LG applying this is just hbar. Remember this. Could you guys write this down? Right? This is so basic. Write this down. This is so important. So then you can see if I use the top ones, this will immediately give us L plus hat mh bar y la. So then you can see I can simplify it this way. Y la. That makes sense? That makes sense? That makes sense? So this is the key idea why we did not use it. We don't like this because we don't know what the YLM is, because we're on the way to derive it. But that you cannot do it. So that's the basic reason. For this reason, we've never been able to use this one. So that's what. In other words, whenever you see these operators, you have to convert that to this shape like this. Okay. And similarly, if you have L hat like this, you always convert to the other one, which is the result. So that's the key idea. So this is the another question. Okay, very good. Now, one last question. What's the eigenvalue of L hat squared? What's the eigenvalue of L hat squared? We have L squared. What's the eigenvalue of this guy? Toby, do you have an idea? L squared equals eigenvalue of this guy.
Just zero.
Okay, 0. Yeah. Okay. Aisha, can you help?
Is that the L times L plus 1?
Yes, did you hear it? So that's the L plus 1 h bar squared. And this is eigenvalue. Now these are absolute basic eigenvalue for the LZ, eigenvalue for the L squared. This is absolute basic. If you can ignore the rest of them, but these two must be remembered. So just remember, eigenvalue of this L squared is L times L plus 1 and h bar squared. So don't forget about h bar squared, because that's the angular momentum itself. Okay, I think that's all that we have. So last time we tried to understand this particular features, as you can see here. So the entire derivation is really depends on the key idea. So now it's time for us to understand what is actually happening here. So we're going to go. So this is the just show you the basic physics part of it, and also show you what that is. So we will keep on going on this until we understand the entire physics part of it. So now, what we want to show you, this is, just keep in mind, what we said last time, this is an eigenstate of L squared and LG squared. I'm going to write over there. Repetition is always not bad. So I want to emphasize just follows the item A. So in other words, I will write out explicitly what these are all about. So they are so important because it just shows how much we need to cover. And let me look at the quality of my camera. Yes, I need to move this side a little bit. Okay, so now I want to be extremely precise. The common eigenfunction of L hat squared, LZ squared, they are YLM. So that's the common eigenfunction. Now when you have an eigenfunction, so there's a no uncertainty. So there's no uncertainty. So there will be no uncertainty whatsoever. Because the eigenstate, remember, there's 0 uncertainty. If you made it 10 times, you get the exact same result. You won't see a different result. And I want to impress you a little further. Suppose my L equals 1. And then I want to measure how large LZ. so-called expectation value or eigenvalue, how large this one is. And I also can calculate how large LZ this will be. If L equals 1, then this will be 1 times 1 plus 1 h bar squared. So this is the eigenvalue that I was talking about, and L plus 1. So this is going to be 2 h bar squared. Now LZ is not a single value. It has 3 different values, because LZ and M can be taken around 3 different values. If M equals 1, then my LZ is going to be h bar itself. It's 1 h bar. And it also can be equals 0 and then 0 h bar. And negative 1, negative h1 bar, like this. So this is the, you see, my M always runs from positive L all the way to the negative L. So each step will be reduced by 1. So that is the eigenvalue. So this, I know the precise result of this. And any question on this? Any question on this? Any question on this? If you do not have a question, I have a question for you. If you didn't have a question, I have a question for you. Did you see I have a M equals 1, 0, and negative 1? Why do we have 3? Why do we have 3? What's the reason why we have 3 of these? It can be 0, it can be 1, or it can be negative 1. Why do we have this? Any idea why we can have this? Cody, why do we have L equals 1, why do we have 3 of these? Yes?
Is that spin up, spin down, or no?
No, that's electron spin, but this is orbital only for the moment. Okay. Any idea why we have 1, 0, negative 1?
Because the different orbitals are affected by the magnetic field.
Yes, the effect of magnetic field. Now let me give you one more hint. This LZ itself is a vector. You remember it's a vector? Vector has directions. Vector has direction. Make sense? So now the reason why we get this, because LZ is a vector. LZ is a vector. Vector can have projections. For instance, if I show you this is my z-axis, suppose this is my z-axis, and then now my xy could be here like this. Sorry, I overlapped this just to save my space. So essentially, I could have x, y, z. Now, I can align this z directly in this orientation and give me 1 h bar. Or in this orientation, give me 0. Make sense? Or this orientation gave me negative 1. So therefore, here is positive 1, here is negative h bar, and here is 0 bar, 0 h bar, like this. And you must think about, but Dr. Zhou, what about these spaces? You only tells me up, here, there. But what about the rest of these ones? Yeah? Is that true? Is that very, here, there, or 0? But why not something between this? Make sense? Make sense? So why something between this? And this is what we call the vector quantization. This is called vector quantization. In other words, we have vector quantization, which means I cannot rotate arbitrarily. No, you either go this, like this. That's called quantization. That's what it means. It's very different from energy quantization. Energy quantization, it's the n number, it's going to be different. They are discretized. But the vector quantization is especially different. Remember, even in the common eigenvalues, already eigenvalues, eigenstate, but I still have 3 of these because the vector quantization. So this is the fundamental reason why I have 3 of these. So again, when we say, you got it?
Yes.
When we say there is no uncertainty, we did not say the LZ can only choose one value. You see, that's the non-trivial part. When we start non-uncertainty, what we mean is the following. If LZ, what you calculate squared, calculate expectation value of this minus the expectation value of LZ squared, and this equals 0. So the no uncertainty, it really means this equation equals 0. Does that make sense to you? Same thing when we say uncertainty, this is LZ squared, L itself squared put over here, and there is no uncertainty. What that means? It does not mean you cannot choose any different values. So this is why the quadrant has a trick here. You said no uncertainty, but here's uncertainty. I would change the word. It's called vector quantization. You see, that's why they started changing these languages, and then you realize there is because they're changing the topics now. They did not say this is a regular quantization. This is a very important one. So far, there is no uncertainty. What it means is this. And this is my part A. What about my part B? Part B, I'm going to write over here. Where's my eraser? Here's my eraser. So part B, I'm going to write over here. This time, we're going to talk about Lx and Ly. This is really funny. So this is part B. Uncertainties in Lx hat and Ly hat. So this is the true uncertainty. In other words, the one that I just showed you a minute ago won't survive anymore. So essentially what I'm saying here, there will be uncertainty in Lx and Ly. So Lx and Ly have uncertainties. So this means if we calculate Lx squared minus Lx squared, this is not equal 0. So there is uncertainty involved. Similarly for the y, well, same thing, not equal 0. So this we will have uncertainty involved. Let me quickly show you Lx. If we calculate Lx, and this Lx is going to equal 0. And I want to show you why this Lx equals 0. So I'll prove this one here. So Lx plus ILy, this is called L diagonal, like this. And Lx minus Iy, then minus like this. Now you see, my Lx is just basically add these two up, divide by 2. So this is my Lx equals 1/2. So this is what I have. Now you see, if you plug in this operator, this operator, when I use this, these operator are this states, not operator. It's just y. So this is just y. I just basically do the interval itself. Now you see, the rising and lowering operator change this y, indices. When they change indices, but left-hand side it does not change anything. So therefore, the evaluation is going to be 0. I skipped this step quickly. I hope you guys follow me. In other words, if you suppose you calculate L plus, then if you apply them on this guy, and then one of these quantum number is going to be changed. So, but when you do the intervals on the left-hand side, you have y, Ln. On the right-hand side, you have y prime, n prime, like this. And L prime, L, n, and n prime, they may not be equal to each other. So that's why it gave you 0. So this is the main reason why we get 0 there. Okay. I skipped this step because it just obviously should be straightforward. And you get the same results, Ly hat equals 0. So this is also same result. And then if this equals 0, so this means this equals 0. Whatever this is a non-zero, you get a non-zero, right? So that's what happens. It turns out that the funny thing is the following. Here's a real funny. And you have found something which is quite counterintuitive. And when you have these uncertainties, And these two actually cannot measure simultaneously, which is now what I'm going to show you. And this part I need to derive very, very carefully for you guys. So this is the equation which we used in this format. And now what I want to show you, I move this LZ to the right-hand side. L hat squared minus LZ hat. So there's no question about that. Now suppose I want to calculate expectation value of this particular operator on the left. So then I will apply, folks, I would change this, the bra itself, change to Ln. And this Ln just equals the YLn just equals YLn. So they're exactly the same. Just for your notation, because I hate to write Y all the time. It's just saving my time, just YN. Now we now see the angle brackets, which means I need to do the angle now. So this will be Lx hat Ly hat squared Ln. So I'm calculating expectation value of these two terms together. And that is what we want for the moment. Now what we want, we can keep on going. Folks, can I erase this part? I just want to need this. I just want to show you what this is. Just represent this. I'm going to erase this part. Okay. So I'm going to erase this now. And this part just equals Ln. I'm going to leave a little more space here. And L hat Ln minus Ln Lz square Ln. So I didn't do anything except just both sides the integral and then multiply this way. So that's the equation that I will be able to get. So, folks, tell me what is the value of this guy's here, Cody? Ln L squared Ln, what this is? Expectation value of the in eigenstate L squared. Look at the board. We have that on board. You found it. Did you find it? Tell me, did you find it where that is?
The eigenstate?
Eigenvalue of LZ. L squared.
L plus 1.
Did you get it? So I told you 5 minutes ago, so just remember this. So that will be L plus 1 hbar squared. Tell me, what about the second term? What is this term is going to give us? Lz squared. What will it be?
That'd just be hbar squared 0 or a.
No, I just want you, I have an m there. M hasn't determined yet. I have an m. In other words, let me give you a little hint. In other words, I want you to know how large this one is going to be. How large this one is going to be. Or in other words, how large this one is going to be. The eigenfunction of Lz equals that, how large that will be. It's also on the board, by the way. Also on board, by the way.
Oh, is it just LH bar?
Yeah, I only interested in Lz applied on the Ln equals what? Okay. I think Aisha must know it. Do you know it?
The image bar.
Exactly here. hbar. Okay. Infamous hbar. Did you see him again? Did you see this guy? Did you see
I thought
this?
that's when it was only applied on YLN.
Yeah, this time, this is because that's LZ applied to YM just equal this. You got it? You got it? So that's why when you apply it on this, so this term apply on this, you see it. You see this one. This one right here. So apply to ym, this is mh.
What was confusing me was this part.
The angle brackets itself?
No, like this part in front of me.
Oh, yeah.
Because like
Okay.
we have the eigenvalue of L squared.
Now this one already show you a list all these. If m equals 1, you get this, m equals 0, you get this. But there is a generic equation, which is m. That makes sense?
Yes.
Okay. And sometimes it's confusing. Yeah, but it's good confusion. All right, so you got this. Now, you figure you understand this, right? You think you understand this. Now let me try it further. I hope you understand this. Go ahead, help me. What happens if I apply this L, Z onto this ones? What will get? What we will get? Cody, you must tell me what you will get. Apply another L, Z onto the same function. What you will get? Just look at the board. There's no need to look at the notes. What? You know, I now have an actual LZ applied to this whole thing. You see, without extra LZ, you understand. But now when I apply another extra LZ onto this, what you will get to this one here? Very important. See whether you. Toby, can you help?
Just another image bar.
Exactly. That's another image bar.
I mean, I don't know. I guess I was complicating it too much for myself.
Yeah, you don't want to do complicated. It's just another image bar. Yeah, it makes sense. It makes sense. So you can move this image bar to the front, because it's just a regular number, the LZ hat LM. And then you're repeating this whole thing again. So this will be MH bar, another MH bar LM. And so this is where you get m squared h bar squared. Makes sense? That's where m squared h bar squared. So in other words, what I did from here to there, this just got m squared h bar squared. Like this. So that's it. And that's all you have. So in other words, just to be sure you know this, you aware of this, how do we do the calculation? That's sure. Now if I apply this LZ 10 times, what do you get? You m to the 10th power, make sense? H bar, 10th power, that's it. About 20 times, wow, 20 times. That's called eigenstate. That is the main reason. What eigen means, it's exactly the same state. You applied it many, many times, and it gave you exactly the same results. So you won't be able to see any difference whatsoever. That's called eigenstate. Otherwise, we won't call it eigenstate because. So this is the main reason why we call it eigenstate. All right. So that's good. I hope this is helpful. So now you notice that if you add these two up, and this is determined. So this is determined. Because if I tell you how large my L is, how large my M is, and this is determined. So the uncertainty, what I was talking about, is that if you calculate individual Lx or individual Ly, there's uncertainty. But if you add the squared up, there's no uncertainty. So this means that my component at the xy plane are not independent of each other. If you measure Lx versus Ly, we'll get entirely different results. So this is the understanding is the following. So here's the understanding. And this understanding is quite important. So this means that if we measure Lx, not Lz, forgive me, and Ly at the same time, each cannot be determined it cannot be determined without exactly without any uncertainty. Each, if you want to measure each, you can. But if you measure them both, you can't. So essentially, what that means is just L squared, x squared. So this means, so this is called uncertainty. So the uncertainty relation, the fundamentally, if you add them up, there is no uncertainty. But so essentially what that means is the following. So the Lx in the Ly, whatever the direction you choose, Lx, Ly, if you measure these two components in the xy plane, you cannot be precise measured. So this is, and this is due to uncertainty principle. The more fundamental reason is the following, because Lx hat Ly hat, this equals IH bar LC hat. And this is what we want to remember. The fundamental reason is because there is uncertainty relation. So I want to use the remainder time for you guys to work on the quiz today. So, and I'm going to stop here. So we're going to start with the quiz. So this is the, let me stop.